In this movie, I'm going to show you how to actually calculate the resting membrane potential of a neuron. So how does one calculate the resting potential in a cell? The membrane potential is given by the Goldman-Hodgkin-Katz equation, abbreviated GHK. The GHK equation calculates the equilibrium potential for each of the major ions, sodium, potassium, and chloride, and then weights each of the equilibrium potentials by their relative permeability. So for example, let's take the membrane potential, Vm, and that's going to be equal to 58 times the log of the concentration of potassium on the outside divided by the concentration of potassium on the inside, plus the concentration of sodium on the outside divided by the concentration of sodium on the inside, plus the concentration of chloride on the inside divided by the concentration of chloride on the outside. And each of these values is going to be weighted by a relative permeability. By the permeability of potassium, the relative permeability of sodium, and the relative permeability of chloride. That's really all it is. I just want to point one thing out to you, and that is the ratio of chloride is reversed. That is, it's the concentration of chloride on the inside over the concentration of chloride of the outside, which is different from sodium and potassium because they're on the concentration of the outside over the inside. This is a minor point, and it's reversed only because chloride is negatively charged. It's a minor point. Don't worry about it. Just realize that chloride is different. So the Goldman-Hodgkin-Katz equation takes into account the relative permeabilities of the three major ions for calculating the cell's actual membrane potential. And in the lower portion of the figure are given the concentrations of the ions in a particular animal called the squid axon. And we're going to consider the squid axon later on, and you'll see why it's important. For now, the intracellular concentrations of potassium, sodium, and chloride are given. The extracellular concentrations of potassium, sodium, and chloride are given, as are the relative permeabilities. And notice the permeability of potassium is 1 because it's the most permeable ion. The permeability of sodium is only 1/100th of potassium. That is, it's 0.01. And the relative permeability of chloride is 0.1. That was determined. It has to be given to us. That's the only way we could know it. So now, let's actually calculate what the membrane potential would be. But before I do that, I just want to calculate the potassium equilibrium potential simply to contrast or show you the difference between the potassium equilibrium potential and what the actual resting membrane potential would be. So to calculate the potassium equilibrium potential, we only use Nernst equation. It's that simple. And the Nernst equation is equal to 58 times the log of potassium concentration on the outside divided by the potassium concentration on the inside. And we know what the potassium concentration of the outside is. It's 20 millimolar. We get it from here. And we know what the potassium concentration on the inside is. It's 400 millimolar. It's given to us in the chart up here. So we simply divide 20 by 400, and that gives you 0.05. So it's 58 times the log of 0.05. And the log of 0.05 is minus 1.3. So we simply multiply 58 times minus 1.3, and voila! We come up with minus 75 millivolts. That is the potassium equilibrium potential given these concentration disparities of 20 millimolar potassium in the extracellular fluid and 400 millimolar in the intracellular fluid. So now let's actually calculate the membrane potential. Remember, the membrane potential is given by the Goldman-Hodgkin-Katz equation, which simply takes each of the equilibrium potentials for each of the ions and weights them by their relative permeabilities. So let's see how this is done. It's not hard. So the membrane potential is equal to 58 times the log of the concentration of potassium in the extracellular fluid. We got that before. It's 20 millimolars divided by the concentration of potassium in the intracellular fluid, which is 400 millimolar. We got that before also, plus the concentration of sodium in the extracellular fluid, which is 450 given on top. We had to get it from somewhere, divided by the concentration of sodium in the intracellular fluid, which is 50 millimolar, plus the concentration of chloride intracellularly, which is 40 millimolar, divided by the concentration of chloride in the extracellular fluid, which is 560. Okay? Next, we deal with the relative permeabilities, and the relative permeability of potassium is 1 because it is the maximum permeability, and everything is taken relative to potassium. So the permeability for sodium is 1/100th that of potassium, so it's 0.01. And the relative permeability of chloride is 1/10 of potassium, and it is 0.1. So now what we're going to do is just multiply these terms. That's it. So it's going to be 1 times 20, which is 20, and of course 1 times 400, which is 400, and then 0.01 times 450, which is 4.5, and 0.01 times 50, which is 0.5, and then 0.1 times 40, which is 4, and 0.1 times 560, which is 56. And then we're going to add them up. So 20 plus 4.5 plus 4 is 28.5. And 400 plus 0.5 plus 56 is 456.5. And we just divide them, and we get 0.062, and we take the logarithm of 0.062, which is minus 1.21, and then we just multiply minus 0.21 times 58, and voila! We get the resting potential. It's minus 78 millivolts. And I point out that the resting membrane potential of minus 70 millivolts is slightly less negative than the potassium equilibrium potential of minus 75 millivolts. And the reason for that is because the contributions of the other ions distracts from the potassium equilibrium potential. So the Goldman-Hodgkin-Katz equation takes into account the relative permeabilities of the three major ions for calculating the cell's actual membrane potential. The resting potential is about minus 78 millivolts. The potassium equilibrium potential is minus 75 millivolts. That would be the membrane potential if the cell were permeable only to potassium. And the sodium equilibrium potential is plus 55 millivolts. This would be the membrane potential if the cell were permeable only to sodium. And you might try calculating that for yourself. It's not hard. And the chloride equilibrium potential would be minus 66.4. This would be the membrane potential if the cell were permeable only to chloride. You also might try calculating that for yourself. It's not hard.